Okay, someone just confirmed that you can see my slide?
Yep.
All right.
Looks good.
If you give me just a moment, I will, I cannot mouse to that thing. I don't know if people have been sharing video, but I turned on my video. I'm Tom Uram from Argonne Leadership Computing Facility, and I'll be talking about Connectomics today. I'll start by telling you about what Connectomics is, but just so that you have an idea, the image that you see here, even though it might make you squeamish, it's a picture of a mouse brain, but it's a reconstruction of a mouse brain, just the vasculature, and it's not a real mouse brain. So if you are squeamish, you shouldn't be. It's just cleverly colored to look convincing. So be at ease. So what is Connectomics? So what we're doing is trying to understand the connectivity between neurons in the brain. And I'll go into some details about this, but the reasons why we want to do this are to understand how the brain works. So how does it achieve its functionality? We often say we all have brains, but we don't know how they work. I suppose for some of us, that's true also of our TVs or something, certainly not of our computers, for example. But we don't know how consciousness arises. We don't know how things change over time. In terms of learning, we don't know if learning arises from, say, a fully connected brain, or if it arises out of new connections that are made in the brain, or just connections that are strengthened. We don't know how changes happen as we age and how that's reflected in the structure of the brain, or if it's only reflected in signaling. In people who have brain injuries, for example, they can have a part of the brain that's responsible for some functionality that is injured, damaged, and another part of the brain kicks up and takes over for that, which implies that it's not static in terms of functionality. So that complicates the questions to some degree. And aside from understanding how the brain works itself, then we can ask questions about things like, given an understanding of biological brains, can we use that to improve neural networks? If we understand how the brain computes, can we use that to build better computers, neuromorphic computers? The brain is tremendously powerful, but also tremendously energy efficient. So there's a lot for us to gain. So just to give you an overview, we'll talk about learning, but to give you an overview of how we get to the data that we care about, I'll take this example of a mouse brain. A mouse brain has approximately 70 million neurons and is about a centimeter cubed. Today, the challenges that we're facing are on the order of a millimeter cubed. So we take a small chunk out of a mouse brain and then cut it into sections that are approximately 40 nanometers thick. So you see here that we're getting to with 6 nanometer resolution in X and Y, and with 40 nanometer thick sections, we end up with 25,000 sections. The sections are imaged on an electron microscope. Each section is imaged in individual tiles, which then have to be stitched together, which you see happening on the rightmost two images. And so how much data do we end up with from a millimeter cubed of a mouse brain? It's approximately a petabyte. So we're already at the order of significant data set sizes. I'm sure you've already learned through ATPESC in the prior days that at Argonne we have approximately 200 petabytes of storage. It was deployed recently. Before that, we were on the order of tens of petabytes, so a petabyte was already a significant amount. And what happens downstream of that physical processing and imaging of this data, after we have stitched sections together into, again, one large section from multiple tiles, what we see as we go through the depth is that the structure changes, right? So imagine slicing through a right cylinder going through the depth, and of course there would be no variation as you go through the depth. But when you have biological objects, there's much more variation. And if we're going to try to trace those objects through the depth of these sections, then the first step is that we have to make sure that they're properly aligned with each other so that we can effectively trace the boundaries of these objects. In this next step, we mask out non-target objects. So for example, here we're interested in neurons and their connectivity. On the title slide, the image was of vasculature, right? So blood flow. And we're not interested in those things. And fortunately, they're much larger than the things that we do care about. So we can mask out a significant fraction of the objects that we need to segment and reduce the workload. Having done that, then we want to segment the remaining objects, the neurons, in each section. And once we've done that, we can assemble these segmented slices back into 3D objects. So if we take an example, we get a 3D representation of a single neuron. In this case, it's really just the cell body of the neuron, no axons, dendrites, connections to other neurons, which then starts to look more like this if we include multiple cell bodies only in this visualization. And you start to see that it's messy and things begin to reveal how they might be interconnected. In this image, I just filtered out all of the reconstructed neurons that had fewer than 1 million voxels within a small subset of the volume that we are working with. And you see the complexity that we begin to deal with, as probably you'd expect. A nicer image showing a fraction of a column is here from a paper from our collaborator at UChicago. And in this case, this is interesting, and it's a visualization accomplishment, but you get an idea of sort of the, excuse me, the density, again, from this image. So looking at learning challenges, I mentioned some of these things, and we'll talk about them in a little bit more detail. So on the left, when we're masking out objects that we don't care about, for example, blood vessels, we will use a 2D UNet to identify those objects. In this case, the 2D UNet identifies these objects fairly well because they differ in contrast from the other objects that we care about. So with lightweight training and inference, we can quickly produce a mask of the objects that we want to omit. In that second image, you see segmentation of the objects we do care about, which was shown on the previous slide. And in this case, we're looking at neurons and their interconnections. What I didn't say here previously was that, like with any learning task, there's a significant effort, human effort in preparing a training data set. And excuse me, while in some data sets it might be easy to just identify cars or cats, the objects that we care about are very irregular, and tracing them is laborious for humans involved. And so there's a lot of work that goes into that. And then we, on top of those annotations, we can train the model. In this case, we're using flood filling network developed at Google, which can, excuse me, I'm sorry, which can recognize the shape and the boundary of these objects to trace them. And once that model is trained to sufficient accuracy on the training data, we can carry that into inference. Now, you can gather from what I've said that training is human intensive. Therefore, our training data tends to be smaller and our volumes are very large. So inference becomes a very compute intensive task. So once we have the trained model, we run it at very large scale on the Argonne systems and produce, in general, segmentation in 3D of all of the neurons within the sample that we care about. ML is not perfect. And so even having that initial segmentation, it doesn't mean we're finished, not at all. The ML segmentation has errors that need to be corrected. And currently, the human effort involved in staring at 3D reconstructions and correcting errors is very significant. We're looking at thousands of hours of human time to correct a single data set. And remember that the scale of data sets that we're working with are much, much smaller than what we expect to encounter in the future. So this significant human effort in terms of annotating and correcting segmentations can't possibly scale to future data set sizes. This is in segmentation, but that also bleeds over into, once we're given that, we get a connectivity graph. So this is just telling us about the individual objects and how they propagate through the volume, and then how they interconnect through synapses. Synapses are identified by a separate 3D unit. So it's trained on, again, hand annotated versions of what synapses look like between neurons. And that produces this connectivity graph. And at this point, again, we have humans staring at the connectivity graph and saying this is not a biologically realistic object, and they're correcting it. So there's more effort in terms of producing a connectivity graph that makes sense. So what are we doing in this space? So I mentioned FFN was developed by Google. So Google themselves are very active in the space of connectomics. They developed the FFN model and continue to work with researchers in this space. FFN is a network developed in TensorFlow. It's open source. It uses a sequence of blocks, which are shown on the upper right. So you see these number of layers, each one of them consisting of multiple convolutional layers with value activation and residual connections. And we can vary the number of these modules, just as you would in any other model, vary the number of convolutional layers, but in this case, we're varying the number of these blocks. Typically, we run with 12 layers, and so we get about 500,000 trainable parameters, though we are exploring variation in the results that we get with variation in the number of layers. One thing I'll say is that while during segmentation, one thing that FFN does is distinguish between merge errors and split errors. So this is important because you can imagine that if it identifies two objects and calls them a single object, then downstream when users are correcting that, they would need to actually trace the boundary between those two objects. But if it's supposed to be a single object, but we identify it as two objects, the user just has to say these two belong together. And so the task of proofreading the data after segmentation is much, much simpler. So FFN takes this into account by preferring these split errors over merge errors. So there's some more details here. Part of the task that we face is, of course, a learning task, like I'm describing, but also in preparation of these samples, we talked about slicing and imaging. We didn't talk about how they're physically prepared before that, how they're stained for imaging, and these things all affect the downstream images and therefore also affect the results that come out of segmentation from the FFN model. And just to clarify, it might mean differences in contrast between the images, which would make it harder for models to transfer between data sets. It might mean that if the diamond knife that's doing the cutting loses its edge, that there are actually jitters in the slice, or that there are folds within the slice. And so there's work in FFN to try to overcome these sorts of defects within the data. But that upstream physical processing is still a significant part of the challenge in this problem. So FFN does a great job, but it's still very significant computationally in terms of what we do. And to get an idea of how this looks going forward, what we talked about previously was taking essentially a tiny brain and then a small chunk of it, only 1 millimeter cubed, to arrive at this petabyte data set. But a challenge that the community is talking about now is doing the full mouse brain. Of course, we're interested in connectivity for a whole brain, not just a small fraction of it, which puts us at 1 centimeter cubed, which is 1,000 times what we talked about before. So it is on order of an exabyte. This is approximately 5x the storage that we have at Argonne today. And that's for a single brain. So for any meaningful science in this case, we probably also need to think about how many models, how many brains we need to reconstruct to be able to make meaningful comparisons between similar regions, for example. And much farther in the future, we'll talk about human brains, at which point we have 80 billion neurons. It's 1,000 cubic centimeters. And so we're talking about 1,000 exabytes at the resolution I have listed there. There's significant effort that needs to go into preparing our tools and our computing in order to face future challenges like these. And I will say here, when I'm describing these data sets, remember I'm talking about only the raw data, which is a collection of 8-bit images. But the data produced as a result of this during segmentation is much, much larger. So segmentation will be approximately 4 times that size. And then we have other data products like the 3D mesh and the skeleton, which are also significant. I'm going to try to finish up quickly, but I'll mention a couple of other things that we didn't really talk about. So I mentioned tiles, and you can imagine as data sets grow and we have a larger number of these tiles that need to be stitched together, we have to look at how we can do this in parallel. So that's one of the things that we're working on now. We talked about alignment. And so that's another area where we're looking at this. And you can imagine as the image sizes grow, that the task of aligning neighboring sections becomes more challenging. And so we need to parallelize within sections so that we can align fractions of sections at the same time, which also produces another challenge. I say here SEM and MSEM because there are different imaging modalities, which is just another dimension for us to consider in the tools space that we have to handle. We have previously scaled FFN training and inference to thousands of nodes in theta. You have been learning about future systems, so we're preparing for those future systems. Looking at hyperparameter optimizations with FFN so that we can improve the model, both in terms of accuracy and in terms of its performance. And also looking at different network architectures for FFN. So we talked about exploring different numbers of these convolutional blocks, but there's also a possibility of using different styles of convolutional block. And we'll also look at using learning in other parts of the pipeline. It might be apparent to you that there's a potential feedback between segmentation of objects through the depth of an image stack, and then also how those images have been aligned. And so we can use a model here to circularly refine the alignment and the segmentation. And then in terms of speeding things up, we'll look at the impact of reduced precision. And we have been deploying tools developed in the Connectomics community for exploring these data sets that reside on ALCF storage over the web. So instead of, in some cases, producing a segmentation, having to pull it back to your home institution to look at it and to correct it, as I described, that task could take place remotely, and we would never have to move the data, which with data sets of the sizes that we're talking about would be prohibitive anyway. So in the future, we're looking at, of course, much larger scales. Like I said, the problem itself will go to a whole mouse brain and to many brains and human brains. Imaging tech is changing and must change. So there are multiple modalities now, but we look at also higher resolution, which would give us larger data sets, and multi-modality imaging, coupling, say, electron microscopy with X-ray imaging at the advanced photon source at Argonne. And the landscape will change in terms of computing, of course, which is why you're all at ATPESC now, so that you can create the future. So if we look at a rough projection from what we're doing today into the future, I already said a whole mouse brain is approximately an exabyte or an exavoxels. So the sample prep alone, you can imagine the task of physically preparing and staining and slicing a data set of this size, let alone the downstream compute. If we look at a projection from what we can do today of how long it would take for a whole mouse brain on theta, then we come in, I'm going to wave my hands a little bit, somewhere around 50 years on theta, the full system for 50 years. And on Aurora, we're looking at something like 3 years. Okay, I definitely put a tilde there in front of the 3 because this will change in that time, and hopefully we'll do much, much better. which will be absolutely necessary because no way will this project get exclusive access to Aurora for 3 years. So you must. And there are approaches there for us to look into to improve this performance already, but that will continue over the next years. And as I said, we must do that to meet future challenges because here we're talking about only a single full mouse brain, but we have requirements that go well beyond that. That's my last slide. I don't know if you're taking questions or if I've just finished early.
Yeah, we have a couple of minutes. Do people have questions?